uh, there's a kind of a disciplined way of talking about fault attacks. And these are the three axes which Verbaal Descartes logic and Schmidt suggest. I'm just going to say that a lot because it's fun that I memorized it. So the first thing we can kind of classify fault attacks is how do I inject the fault? The method. So what is in my lab? What is in my attacker setting that causes the fault to happen? Right? This is the first aspect. The second one is the properties. So I'm creating a fault, but is this a temporary fault, permanent fault, a random fault, and so on, a reversible fault, and so on. And the third thing is the target. The target is what part of the system am I breaking? Am I breaking the crypto core? Am I breaking the memory? Am I breaking the IOs? Am I breaking the I don't know what? Is everybody clear about the difference between the method and the target? Who understood the difference between method and target? Because it's a little confusing. So method is what am I holding in my hands as the attacker, and the target is what inside the device under test gets affected. So method is the attacker, and the target is in the victim. Okay, so glad that you understand. Yeah, method could be heat, could be sound, could be other crafty things. So toward the end of this hour, I'm going to show you one fault attack, which is actually practical, and we can try to classify it according to this taxonomy. So the first thing, which is kind of exciting and everybody wants to think about, is the method, right? How do we do the fault attack? How do we inject the fault attack? So there are all sorts of very crazy and creative ways of doing injection. And yeah, heat or sound method. So one very popular method of fault injection is messing with the power supply. What is nice about the power supply is that it's relatively easy for you to motivate that the attacker has control over the power supply. No, because simple power analysis, differential power analysis, also assumes that the attacker has control over the power supply. Why so? Why does it assume so? Because we're saying the attacker has to cut the power supply. So if the attacker is cutting the power supply and putting a probe, you can just go to the next step and say the attacker is cutting the power supply and putting some kind of an active jamming, targeting stuff. So if you have control over the power supply, what can we do? The two things we can do is give less power and give too much power. So giving less power is called undervolting or blackout, or blackout is when we give no power, and brownout is when we give a little less power than we wanted to. And what happens if you give Tempest is a passive method. Tempest is a side channel or reception method. But undervolting, so what happens is there are bits, the registers in the device. I showed you the CMOS flip-flops. When they turn on, they basically have a random value. But it so happens that the random value is not always random. There are some bits which really like to wake up as zeros, and some bits which really like to wake up as ones, and some bits which wake up completely randomly. And when you lower the power supply to the device slowly, these bits start returning to their default values. And each one of these bits has a different voltage where it decides I can't contain the value I was supposed to contain, I'm going to reset. So if I reduce the power just a little bit, some of the bits in the device are going to go to the random original values, and some of them are going to stay in the one the programmer wanted. So by undervolting, I can create a fault, very creative fault. Now, the other thing I can do is a power spike, just give a nice bump of power. And when I give a power spike, all sorts of crazy things can happen. What sometimes happens is that a microcontroller decides that it's not going to execute the next command. It's just going to skip it and go on to the next command. If you think about if that command is going to be a conditional jump, and you suddenly don't make this check, then you're in fantastic shape. Now, you're thinking about it, how do I get my power spike at the exact correct time to jump over that jump, then you have to, again, you're getting like into an argument with your systems architect. So this is one thing, very common attack model. The next thing is what is called clock glitching. So clock glitching, I showed you synchronous circuits, and the idea is that the circuits have what is called a setup time. So when the clock edge rises, all of the bits go from the entrance to the exit, and then all sorts of calculations happen, and the new values propagate through the circuit, and then by the beginning of the next clock cycle, the results of all the computations are ready to be used again. If I do a clock glitch, which means if I give a clock which is very, very fast, some of the computations will be finished, some of the computations which are relatively simple, but the more complex computations will not be finished. So again, I will have like a mishmash situation in my device where part of the computations are finished and some of them have not finished, and again, it's kind of a fault in the legal situation. And again, it's reasonable, it's justifiable to have clock glitching because in many devices, for example, in smart cards, the clock is also externally provided to the device under test. So I can justify that I can glitch the clock. In others, sometimes also the clock, excuse me, the cat. מה את רוצה? אפשר לצאת? That was the cat. Thank you. Thank you to the cat. Now, so clock glitching is also something which is justifiable. And now we can talk about another kind of attack, which is the temperature attack. The temperature attack, we just heat the device under test. We heat it. How do we heat it? Anybody have an idea how to heat it? Okay, yeah, we could use a flamethrower indeed. So we can use yeah, small one, right? So we can use a lamp. That's right. You can use an incandescent lamp, not an LED lamp. We can use a lamp. We can kind of also use other components in the system. You know, we can try to hot air fan, but we can try to cause a neighboring component to work really hard, and that will also cause the temperature to rise. And why are temperature attacks false attacks? Because electrons like to jump. They like to jump, and the hotter it is, the more they like to jump. Very, very basic physics parts you just got. And if they jump too fast, they were going to change the states of logic elements in the device. Again, you're going to get some bits flipping, and their program is going to do all sorts of crazy stuff. What's the disadvantage of a temperature attack compared to power supply attacks? Can anybody think? So, yeah, we usually cannot expect the outcome, but yeah, but again, indeed, as what you're saying, the level of control seems low. I'm heating; it's going to take me a long time. I can't give like a blast of heat on a particular microsecond. It's going to be a gradual situation, right? So, I cannot very accurately control the timing of a temperature attack, unless I can think of any way of doing that. But maybe there are other ways. So, and then the final form of fault attacks, which are suggested by this paper, and they are more at home in the lab than in the hands of a serious attacker, in our house, are optical electromagnetic attacks. So this is the frickin' laser beams attack. We take a frickin' laser, it's usually green, and we shine it at a transistor. And then the transistor decides it doesn't want to be 0 anymore because now it wants to be a 1. We can also do it using electromagnetic pulses. And of course, to do that, we need to file, decapsulate the chip and kind of make everything easy to access and maybe mount it on a custom circuit board. This is, if you're writing a very, very secure device, it might be justifiable, but your systems engineer is going to make a very, very funny face at you if you start saying that I don't know, your your ticket of entry to the student fest is going to be subjected to freaking laser beams and cosmic radiation. Okay, so this is a very nice point that Gil mentioned. Um, faults that the study of fault attacks basically comes from what is called the reliability community. There are a bunch of engineers, very serious and mature engineers, who talk about reliability. Um, Reliability of spaceborne systems, airborne systems, and maybe mission critical systems. And faults happen, you know. For example, we have error correcting codes in server memories because sometimes the bits in the server like to flip. So we need to think about how to protect against these things when they occur randomly, and then sure, uh, and then the cyber guys look at it and say, okay, what if we don't have these things happen randomly? What if we cause them deterministically? And again, this is a very very natural progression you see when you study fault attacks. Somebody in the reliability community discovers something which happens very rarely, and then the cyber dudes say, okay, we can make it happen once a minute, and suddenly it's a very serious attack. So all of these things sound like things which are at least as complicated to justify as power analysis. And power analysis is also not so easily justified, right? So this is where we were when I joined the university 4.5 years ago. But two very crazy methods of generating faults came in very recently. And one method of generating fault is a reading from memory. So, yeah, of course, Rowhammer. So I'm going to go into it next week, God willing. But just a briefly to state, if you have the privileges of reading, not writing, reading memory on the target machine, for example, via JavaScript, then you can do fault attacks. And this is a little, this is problematic, right? And another thing, a very crazy kind of fault attack method is running shell commands, or generally executing non-privileged code. And this is the clockscrew slash volt jockey slash blunderbolt family of fault attacks. And basically, again, I'll try to go into this next week if time allows. Basically, you abuse the power saving mechanisms of processors, and you make them save power so much that their internal state starts going crazy because they're turning down the power consumption so much that things stop working. And another thing which is completely crazy, and it's so crazy I don't want to talk about it because these are results from last month, which is what's called speculative fault attacks, also known as LVI. And that may, if we return to the discussion of last week about speculative execution, there is a way of making the CPU speculatively execute faulty instructions. And then it's running these instructions and then saying, oh no, I wasn't supposed to run these commands. Quickly, let's throw them away. But again, using the insights of Spectre, you throw it away, but still you can smell the garlic, right? So, but I won't be able to teach this year. You can read about it yourself. You can also watch, there's a YouTube video about that as part of the IEEE proceedings, which you can see. So these are the methods, and you can think of more exciting methods. I think that Gil was suggesting so charged particles. I would say you're using, if you're using radioactive source, you're suggesting alpha particles or beta particles, which are charged ions, which actually can do a lot of damage. And you can think of other crazy things. Vibrations, for example, if you shout strong enough at the hard disk, it can cause faults. I'm not very clear about how can you use that to get the secrets out, but it's still a fantastic example of the meeting between physics and the real and theory. So we have decided what we want to buy in our lab. We're going to buy a power supply. We're going to buy a clock glitcher. We're going to buy freaking laser beams and so on. And then we are creating a fault. So what are the properties of our fault? So here are some things we can say about our fault. So first thing we can say about is how much control do we have about the over the fault. So we can have a precise fault. And again, the things we can discuss here are the location in memory, the size, how many bytes are we affecting, and at what time are we doing it. So we can say we are going to make a fault that can precisely flip this bit in memory whenever we say, so we're going to look at the execution, and we're going to find out when our CPU is going to do a conditional jump, and we're going to flip a bit to make it take the else instead of the if, and then we can get also to secret test. So this is going to be a very precise attack. But there are also looser attacks. So a loose attack can say, I'm going to flip a bit, which is if it's inside this 4 kilobyte page in memory. So one of the bits is going to be flipped. I don't know which one. I don't know exactly when. But it's going to be in this area of memory. And of course, the worst thing you can say is no control. So you're going to say the device is now it's a little cuckoo, and it's going to do something wrong sometime during the execution. I don't know exactly what it's going to do wrong because I'm not a reverse engineer, but fantastically, there are attacks which can, as long as there's some kind of fault, they can get the secrets out. And I won't have time to talk about it today, but I might touch on it next week. And as in parallel to the control over the fault, another thing is the duration of the fault. So there are 3 cases of faults which the Karl-Schmidt and Wilbauche identify. And you can think if this is the right division or not, but it's very nice to think about it this way. So the first type of fault is transient. What does that mean? I'm reading a byte from memory. I read it, I get 5. I read it, 5. Read it, 5. I get a fault. I read it, what do I get? 4. Great. I read it again, what do I get? 5. I get 5, right? Because it was a transient fault. So I just got to hit one command. And now the next thing is a permanent fault. Permanent fault is a fault which will persist until I do a reboot or a quit, and I stop the program and run it again. So I read, I get 5, 5, 5, I get a fault, then I'm going to get 4, 4, 4, 4, 4. So essentially I flip the bit somewhere in memory, or I change the opcode of one command, or I change like a state, and as long as the computer is still running this program, it's going to stay the same. And now this is the second class, and the third class is destructive. Destructive means I have a 5, 5, 5. I do the fault, I get 4, and then that's all I'm going to get. I'm going to get stuck at 4. I can reboot, I can reflash, I can leave and re-enter the room. I can put it in a bag of rice. It's going to stay broken forever. And of course, again, when you're trying to sell to your systems architect. So what is so please show me what is the thing which the systems architect is going to be the least impressed. I'm going to show me the attack which is going to be the least impressive to the systems engineer, right? So if to get my attack running, I need a precise transient fault, then my systems architect is going to say, fine, but you're not going to have a precise and transient fault, because you can't control the exact location and you can't control the exact time, and it's going to break the system completely. And what is the least, what is the one which is going to be the most impressive to your systems architect? So the most impressive attack is going to be an attack if you're saying, if you give me any kind of fault, and even if this fault is destructive or permanent, I can still get the secrets out. And again, the question is, why do I need a destructive fault? And I think you are very clever in remarking, maybe I want to reverse engineer the device, I want to create a clone of it, or maybe I have like a bunch of devices, I'm breaking one, and then I can use all the others. So, 12 minutes. Let's see what we can do in 12 minutes. I'm going to, you know what, I'm just going to truck through there. I have 2 slides left, and let's see if I have time for BM Shamir, or I'll just leave you to read BM Shamir. It's four pages of genius. So, these are the properties of the fault. And the last thing we have left is the target of the fault. And the target of the fault, I don't really have a lot to say about it, because even admitting that I know what is the target of the fault, I'm giving something away. I'm making my attack with it. But what kind of things can I fault? So one thing is input parameters. This is very close to fuzzing. So I did the fault attack, and now the inputs are wrong. You know, the file is malformed. The parameters are wrong. Maybe I'm trying to hash a string of length 0. Maybe I'm trying to compare. I'm trying to compare something to a value which is known because of the default. So I can break the input parameters. The next thing I can break is storage. So storage, when you think about fault attacks, this is usually what you have in your head. I have memory storage somewhere, and I fault it, and now something else is stored in memory. So I flipped a bit, or I zeroed out some kind of word. And of course, this can be temporary. Yeah, so Oren is saying, why should I do a fault attack on input parameters? So first of all, the answer is that's true. You can provide faulty inputs in kind of a fuzzing, and this is technically a type of fault attack. But you can also, using active fault injection, bring inputs into the functions which it wasn't supposed to get. Okay, so if the function is expecting some kind of let's say there's an input sanitizer, and then your function, and you put the fault after the sanitizer, suddenly your function is trying to deal with input it's not expecting, and maybe you can create a very dramatic fault that way. So storage, and again, you can do volatile storage, which is RAM, or non-volatile storage, which could be the SSD, or flipping something in the SSD. And volatile can also be the registers inside the CPU. So if I'm reading something from memory into the CPU, and then I fault the CPU, the next time I read, I will get the right value from the memory. So this is going to be a transient fault. The next two things, which are very close together, they are data processing and instruction processing. So basically, I'm data processing means, let's say that the device under test is trying to multiply two numbers, and now I faulted it, and it doesn't know how to multiply anymore, and it gives me this kind of random garbage instead of multiplication, and then I need to find out how can I do something with that. You can do something very exciting with that. I'll show you next week. And the parallel of this is control flow. So control flow instructions are special kinds of instructions which don't only affect data, but they also affect what is the next command I'm going to run. And if I fault a control flow, I can not necessarily a control bus. It's inside the CPU. Let's say, for example, I'm stuck in an infinite loop. I fault. I give like a fault, and suddenly I'm out of this loop. A very, very important type of attack, which I'm going to show you next slide. So these are the targets, and you can think of all sorts of targets. Of course, the better you understand the device, you can say, I'm going to do a fault of the cache. I'm going to do a fault of the instruction cache. I'm going to do a fault of the level 1 instruction cache. And the more intimate you get with the device, in a way, the less impressive your attack becomes, because who told you that you're going to get a transient attack on the instruction cache, right? Other best practices. Look, here's the cat again. There are people who work for a living in certifying devices against fault attacks. I don't work there, but I know there are people who are real artists in doing fault attacks. So there are best practices. I'm not qualified to teach them. Right.